Chapter 6 notes the Earth. The Earth. In simple terms, the Earth is a huge rocky sphere spinning in space and moving around the Sun at a speed of about 100 miles every few seconds. Earth also has a blanket of air and a magnetic field that protects the surface from the hazards of interplanetary space. It is the mass of the Earth, you guys, the mass of the Earth that gives us our atmosphere, or that blanket of air. Because of the spin of the Earth, the rotation of the Earth, we have a bulge at the equator. Okay. For an example, if the Earth spin, I know this sounds ridiculous, but if you'd have taken the geology, it'd make more sense. And those of you that have will understand. In 24 hours, the poles only move as much as this circle here. Okay. At the equator, in 24 hours, it moves a lot more distance. It moves a larger distance in the same amount of time. Therefore, there's a higher acceleration on the equator. Because there's a higher acceleration there, it causes a bulge on the equator. All right. And then you can see here, it's about 20 kilometers, 21 kilometer bulge that we get. So about 21 kilometers farther from the center to the equator than the center of the Earth to the poles. The Earth is large enough for gravity to have shaped it into a sphere. Smaller bodies like asteroids and that's why they're not so much spherical. They're more just look like a big boulder floating in space. They do not have enough gravity to crush it into a sphere shape. More precisely, Earth's spin makes its equator bulge into a shape referred to as an oblate spheroid, and this is a result of inertia. Composition of the Earth. These are the elements that make up most of the Earth's surface. Most common elements of the Earth's surface rocks are oxygen, 45% by mass, silicon, 27%, aluminum, 8.3, iron, 6.2, calcium, 4.66, and magnesium, 2.76%. Silicon and oxygen usually occur together as a silicate. Ordinary sand is the silicate mineral quartz and is nearly pure silicon dioxide. The other thing here too is living organisms. We use carbon as our chain, and silicon can be used also. It's the only other element where that can have four other atoms hooked to it. I will show you in the notes, or the notes in the lecture. I'll draw it out so you can see what I'm talking about. But all non-organic material, well, I don't want to say all, but most have silicon as its central atom. Density of the Earth. Density is a measure of how much material or mass is packed into a given volume. How close are those particles? Typical units of density is grams per unit centimeter or per cubic centimeter. Water has a density of 1. Ordinary surface rocks are 3, while iron is 8. For a spherical object of mass and radius, the average density is given by this equation. The mass divided by 4/3 of pi times the radius cubed. For Earth, this density is found to be 5.5 grams a centimeter cubed. So the average density is 5.5 grams a centimeter cubed. Consequently, the Earth's interior core is probably iron, which is abundant in nature and high in density. The Earth's interior. Earthquakes generate seismic waves that move through the Earth with speeds depending on the properties of the material through which they travel. Again, you would have learned this in the geology class. The other thing I want to say is it says earthquakes here. That's not always the case. That's part of the reason when North Korea here in the past few years was testing out their nukes to see what would happen. It kind of upsets the scientific world because this is a perfect time. If we know it's going to happen, and usually when a country is going to test these things, they'll say something to the scientific world so we can check out the seismic waves that the atomic blast or the nuclear blast creates. All right. But if we don't know when it's going to happen, we can't really use that. So it says earthquakes here, but a lot of what we know are from you practicing nuclear bombs, dropping nuclear bombs. So the speeds, because they cause seismic waves. The speeds are determined by timing the arrival of the waves at remote points on Earth's surfaces. The seismic picture is then generated of the Earth's interior along the path of. So here's a sonogram of the Earth. And notice it's showing an earthquake here that could just as well say a nuclear practice bomb. All right. And notice this is the only way we have to probe the Earth's interior. So we have two different types of wave. We have P waves and we have S waves. Now, P waves will travel through water. They'll travel through liquid. They travel through all material. S waves, on the other hand, do not. Okay. And since they do not, when we have, and I should state too, that an earthquake or a nuclear blast, whatever, gives off two kinds of waves: primary waves and secondary waves. The P waves, or the primary waves, travel out from the epicenter of the earthquake or the blast, and they will, in the center, in this liquid part, they get diffracted. They change a little bit, okay? But they still travel to the other side of the Earth. They'll change or get diffracted by a liquid or a center, a core like this. And we know that it is a solid core because you notice, again, it diffracts, it speeds up. The particles are closer to solid, so the center part that's going through the solid of these P waves is going to bow out even more and distort the wave even more. But P waves will travel through liquids, solids. These two zones here, where we see no waves, are known as shadow zones. That just means we don't see the waves there. Now, S waves, or these secondary waves, cannot travel through a liquid. And we see them in these areas right here. All right. And since S waves cannot travel through a liquid, we're going to assume that there is a liquid core with a solid core in the center of it. All right. Now you can see, if this is the only way we have to study, why we get upset. The scientific world gets upset when other countries tell us that we are not, or they don't tell us when they're going to use these bombs and stuff like that practice. So we can't use our scientific meters and that to pick up the waves. A little more about S waves and P waves. P waves compress material and travel easily through a liquid or a solid, where S waves move material perpendicular to the wave direction of travel only, and they only propagate through solids, or they only travel through a solid. And you can see here, our P waves come through like this, all right? And the energy is moved along this spring, we'll just call it a slinky, in this direction. S waves, on the other hand, fluctuate at right angles. Notice, right angle. Right angle. These are the waves that cause the damage because they go this way, and as the energy moves, it also is going like this, and it shakes the ground back and forth, and that's what causes all the damage. So S waves and P waves, again, the big thing here, S waves do not travel through liquids, only through solids. So I kind of explained this in the previous slide. If you see, there we go. So observations show P waves but no S waves at detecting stations on the opposite side of the Earth from the origin of the earthquake. So the Earth has to have a liquid core. All right. And that liquid core is proven by S waves not traveling through the Earth's interior. So, with all this in mind, on the Earth, we have a crust, a mantle, a liquid core, and that solid inner core. A solid, low density, and thin crust made mainly of silicates. This is where most of our silicates are on the surface. And then we have a hot, thick, not quite liquid mantle, which is here. A liquid outer core with a mixture of iron, nickel, and perhaps sulfur, and a solid inner core of iron and nickel. Okay, here they are. And here are some of the elements that make up these areas of the Earth. So that brings on, when we're looking at these and the different elements that make up these layers, this is known as differentiation. All right, the Earth is layered in such a fashion that the densest materials are at the center and the least dense materials are at the surface. This is referred to as differentiation. Differentiation will occur in a mixture of heavy and light materials if these materials are liquid for a long enough time in a gravitational field. Consequently, the Earth must have been almost entirely liquid in the past. The Earth's inner core is solid because it is under such high pressure from overlying materials that the temperature there is not high enough to liquefy it. This is not the case for the outer liquid core. So I'm going to go back, and what it's saying, the reason this is solid, all right, is because it's not necessarily not hot enough, but it's not hot enough under the situation. And this, again, is some geology for you. This overlaying mass, this huge mass that overlays the center of this, causes the space between the molecules, the space between the atoms to be crushed out of it. So even though it's hot enough for them to be a liquid, they're being forced together by the pressure of the mass above it into a solid. Okay. All right. So here is differentiation in modern terms, or modern, easy to understand an analogy. I love chip mint ice creams too. It's horrible. But if you take some mint chocolate chip ice cream and you let it melt, you heat it to where it melts. This is differentiation. Gravity will pull the heavier material, or the chocolate chips, to the bottom of the container. Look at that leaking out. What a waste. The mint chocolate chip foam will be on top because it does not have the same density. So the more dense materials fall to the bottom. And then they're going to use this to show us how on Earth, when Earth was molten, the heavier iron, the heavier nickel moves into the core. It's pulled out just like this. The more dense chocolate chips, the more dense materials, the more dense elements will be pulled towards the middle of the Earth. Okay, so the temperature inside the Earth, heating the Earth's core. The estimated temperature of the Earth's core is 6,500 Kelvin. This high temperature is probably due at least to the following two causes: heat generation from the impact of small bodies that eventually form the Earth by their mutual gravitation, and then the radioactive decay of radioactive elements that occur naturally in the mix of materials that make up the Earth. Okay, so the radioactive material in the Earth heats up the core. And that, before I go to the next slide, that's contrary to what we're told in physical science. In physical science, the only energy comes from the sun as far as we are concerned. But there is energy inside the Earth's core that doesn't come from the sun, and that is radioactive energy, radioactive decay, and radioactive elements. So, the cooling of terrestrial bodies. How did that Earth cool off? It takes a long time, guys. In either case, the thermal energy generated is trapped inside the Earth's interior due to the long time it takes to move to the surface and escape. So it takes that a long time to cool off. All right. And I'm not sure what this is here other than to say, hey, look, a 1 meter cube is going to cool off a lot faster than this because the Earth is deep. It's, I mean, 1,200. We saw 6,000 kilometers, a little more than 6,000 kilometers from the edge to the center. And because of that, or from the crust to the center, it takes a long time. There's a lot of gravity there holding all this in. And it takes a while for that heat to escape and cool things off. So we can tell how old the Earth is by radiometric dating. What is radiometric dating? If I have a chunk of potassium, 100% potassium, and we're just going to say it'll be easier if we just say that we have 100 atoms bound together, making this little chunk of sodium. It'll make it easier to understand. So we have 100% or 100 atoms of potassium. This is when it first forms. After its first half-life, and the half-life is 1.28 billion years, we have 50 potassium atoms. And because potassium is radioactive, this isotope is radioactive. After 1.28 billion years, I end up with 45 calcium. Some of these calcium also turn into argon. So I have 50 atoms of potassium, 45 of calcium, 5 argon. Another half-life goes by, 2.56 billion years now. We're looking at only 25 atoms of potassium. 75 of them have broken down into these other substances or these other elements. Calcium now, and then argon, all right? If I go through another half-life, 12 potassium, 79 calcium, 9 argon, and finally another half-life gives me 6 potassium, 84 calcium, and 10 argon. When we're out there in the real world, in geology, and we're digging these stones, this is the kind of thing we find at this time. It looks like it's calcium, but it has some argon and potassium in it too. Where did the argon and potassium come from? Boom, 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 boom. Well, 5.12 billion years ago, this is what I actually had. 5.12 billion years later, it turned into this, okay, because of radioactive decay. Radioactive decay is used to determine the Earth's age. Radioactive atoms decay into daughter atoms. The more daughter atoms there are relative to the original radioactive atom, the older the rock is. Radioactive potassium has a half-life of 1.28 billion years and decays into argon, which is a gas that is trapped in the rock unless it melts. Assume rock has no argon when originally formed. Measuring the ratio of argon atoms to potassium atoms gives the age of the rock. This method gives a minimum age of Earth as 4 billion years old. Other considerations put the age at 4.5 billion years old. Again, a little more geology, motion in the Earth's interior. Heat generated by radioactive decay in the Earth creates movement of rock. This movement of material is called convection. Convection occurs because hotter material will be less dense than its cooler surroundings and consequently will rise while cooler material sinks. Remember, as an object heats up, it expands. As it expands, it becomes less dense, all right? And less dense material will rise to the top. And this causes these convection currents, all right? These convection currents. Now, you can see if I have on the crust land masses or plates, how these plates will move. And I'm sure that's where we're headed with this. Okay, we're going to go and talk about plate motion, plate tectonics. But these convection currents cause the plates to move like this across the surface of the Earth. But we have that convection current deep inside. Convection in the Earth's interior. The crust and mantle are solid rocks, although when heated, rock may develop convective motions. These convective motions are slow, but are causes of earthquakes, volcanoes, the Earth's magnetic field, and perhaps the atmosphere itself. So this is going to help you right here. Look at the soup. It's going to show soup. This slide here could have an answer to one of the homework problems. We also have rifting. And what rifting is when this hot material rises up to the surface. It breaks through the surface. What's happening here? Sometimes we'll call it like a seafloor spreading. This material is pouring out here, and as this material pours out, it pushes these plates. You can see it right here, pushing these plates from one direction away from each other. This is causing the seafloor to increase in size and push these land masses away from each other. Hot molten material rises from deep in the Earth's interior in great slow plumes that work their way to the surface. Near the surface, these plumes spread and drag the surface layers from below. GPS measurements show the continents moving up to 10 centimeters a year relative to each other. So the Atlantic Ocean is we'll say the Atlantic Ocean is moving 10 centimeters, growing 10 centimeters per year. It's getting 10 centimeters wider per year. I believe these rising materials, these rifts, this is just off the top of my head. There is between, I believe, 30,000. Now, you got to think there's a lot more ocean than there is landmass. I believe there are between 30,000 and 100,000 undersea plumes active right now at any one time, between 30 and 100,000. We used to think it was about 3,000, but with all the new remote vehicles and all that, we've discovered there's way more than we originally thought. So now, where this rifting is occurring and it's pushing this seafloor into the continents, I get what's called subduction. The seafloor is less dense, the land is less dense, so the seafloor will sink underneath. It's pulled under. Okay, subduction, where cool material sinks, it may drag crustal pieces together, buckling them upward into mountains. And you can see on the coast of the United States, we have mountains. And that's what's going on. If one piece of crust slips under the other, it's called subduction. Now you note, where's this coming from? What's up with this? The friction from this plate sliding underneath this plate, that friction builds up and it causes magma to form. All right, that heat causes magma, and you get these mountains or volcanic mountains sometimes. And right now in the state of Washington and California, that Mount St. Helens, Mount Rainier, all of these different volcanoes along our west coast where the subduction is happening. Changing the face of the earth. Rifting and subduction are the dominant forces that sculpt the landscape. They may also trigger earthquakes and volcanoes, and they do because this friction right here, this is just not smooth friction. You got to think there's mountains. You can see a mountain here, a volcanic mountain. Eventually, that's going to hit right here, and pressure is going to build up. As this plate, once that mountaintop is sheared or these rough areas are sheared, this plate will lurch forward, causing a earthquake, or along the water like this, possibly a tsunami. Plate tectonics. The shifting of large blocks of Earth's surface is called plate tectonics. Early researchers noted that South America and Africa appear to fit together and that the two continents shared similar fossils. It was later proposed in 1912 that all of the continents were once a single supercontinent called Pangaea. The Earth's surface is continually building up and breaking down over time, scales of millions of years. All right, so when Sider, and I'm not that much older than you guys, okay? I am, but as far as Earth's time goes, not really. We were taught when I was in school, continental drift, that everything just drifted to where it is, okay? Over time, the different continents kind of floated to where they are today. Well, we know better than that now. We know it is plate tectonics. Plate tectonics, you guys, are fairly new. We're talking the 60s. They came up with the idea of plate tectonics in the 60s. So when I was in school, we weren't taught plate tectonics. We were taught continental drift, kind of crazy. All right, the Earth's magnetic field. Magnetic forces are communicated by magnetic field. Direct physical contact is not necessary to transmit magnetic forces. Magnetic fields are depicted in diagrams by magnetic lines of force. Each line represents the direction a compass would point. Density of lines indicate strength in field. So the heavier the line, the more dense the line. One of the other things that we talk about in Earth or in geology too is notice how I have these openings at either end of the Earth. Okay. I have these openings where harmful radiation and that can just come in and hit the Earth. I have, the cool thing about this is I have two great big mirrors at either end, the ice caps. This harmful radiation and that comes in, hits the polar ice caps, and is reflected back out. That's why our polar ice caps are so important. Magnetic field visualized. Magnetic fields also have polarity, a direction from a north magnetic pole to a south magnetic pole. Magnetic fields are generated either by large-scale currents or currents on an atomic scale. This is a cool thing, too, and we're not sure. This is one of those things in science, since there's a magnet on the screen here, I'm going to just hit real quick. If I divide this bar magnet in half, I have a north and a south pole, a magnetic north and a magnetic south. This is what's crazy. If I take this and I cut a chunk off of the north side, like right here, if I take this piece off, this automatically knows to change to a south pole, magnetic pole. We're not sure how that happens. Same down here. If I take the southern half, the southern pole of this magnet, and cut it in half, this will instantly become, as soon as this is cut off, this instantly knows, that magnet knows that it's now a north pole instead of a south pole. Very, very strange, but cool nonetheless. So how does the Earth get that magnetic field? The origin of the magnetic field. The magnetic field of the Earth is generated by currents flowing in its molten iron core. The currents are believed to be caused by rotation of motion and convection, or what we call a magnetic dynamo. The Earth's geographic poles and magnetic poles do not coincide. Both the position and strength of the poles changes slightly from year to year, even reversing their polarity every 250,000 years or so. So the magnetic effects in the upper atmosphere. Notice how the sun comes in and some of the particles are blocked by the sun or by the magnetic field. Earth's magnetic field screens the planets from charged particles emitted from the sun. The Earth's magnetic field deflects the charged particles into spiral trajectories and slows them down. Region of the Earth's environment where the Earth's magnetic field affects particle motion is called the magnetosphere. Within the magnetosphere, charged particles are trapped in two donut-shaped rings that encircle the Earth and are known as the Van Allen radiation belts right here. These Van Allen radiation belts. As the charged solar particles stream past Earth, they generate electrical currents in the upper atmosphere. These currents collide and excite gaseous nitrogen and atomic oxygen. And as the atoms and molecules de-excite, and we know that they give off light, right? Photons are emitted, resulting in the aurora. In the northern hemisphere, the aurora borealis, and in the northern hemisphere, aurora borealis. The southern hemisphere, the aurora australis. How about our lovely atmosphere? A veil of gases around Earth constitutes its atmosphere. Relative to other planetary atmospheres, the Earth's atmosphere is unique. However, studying the Earth's atmosphere can tell us about atmospheres in general. Again, the reason we're even studying the Earth is because just from the very first couple of days in class, we talked about how we compare every other planet in the solar system and in the universe to the Earth, because that's what we have at hand to study, the Earth. So we compare everything, including atmospheres, to Earth's atmosphere. All right. Something you also should probably know, down in this area, most of the atmosphere is held in this area. Okay, the higher you go, the thinner the atmosphere becomes. So atmosphere extends hundreds of kilometers, becoming very tenuous at high altitudes. And the atmosphere becomes less dense with increasing altitude. That means the higher up we get, the farther apart the particles are. Half the mass of the atmosphere is within the first 4 kilometers, and the atmosphere eventually merges with the vacuum of interplanetary space. Just like we have a composition for the Earth, there is a composition of the atmosphere. The Earth's atmosphere is primarily nitrogen, 78%, and oxygen, 21% by numbers. The remaining gases in the atmosphere are about 1%. They include carbon dioxide, ozone, water, argon, the first 3 of which are important for life. This composition is unique relative to the carbon dioxide atmospheres of Mars and Venus, and the hydrogen atmospheres of the outer, larger planets. The greenhouse effect. Visible light reaches the Earth's surface and is converted to heat. As a result, the surface radiates infrared energy, which is trapped by the atmosphere at infrared lengths. This reduces the rate of heat loss and makes the surface hotter than it would be otherwise. What? Okay. I just said that jokingly. What happens is heat comes down and it hits the Earth and it turns into infrared heat. Carbon dioxide in the air, methane in our air traps. It usually comes down and hits and then bounces back out, or eventually it'll radiate back out. But certain gases tend to keep it here and not let it radiate out, as in this right here. CO2 and H2O absorb and re-radiate radiation. So as it hits, instead of radiating out, it'll hit the CO2 in the air and then radiate back down to the Earth and cause this greenhouse effect. Traces of Earth's temperature and atmospheric carbon dioxide content for the past 800,000 years show a strong correlation. Now, I'm just going to tell you, it's important to know climate change, but Sider thinks it's a bunch of bunk. If you would have had me for geology, you'd know I'm on the board with a mini ice age is on its way. A mini ice age is coming, not global warming. They have it wrong, as far as I'm concerned, with the difference. And if you would have taken geology, and some of you have, I know that are in this class, you'd know what I'm talking about. So, traces of Earth's temperature and atmospheric carbon dioxide content for the past 800,000 years shows a strong correlation. Many scientists are concerned that humans are adding so much carbon dioxide to the atmosphere that we might trap so much heat that Earth's temperature will climb, a process called global warming. Again, I don't believe in it. If you really want to know the details of what I think, I can find some papers, scientific papers for you to read. So just let me know if you're interested. The ozone layer. Oxygen in the atmosphere provides a shield against solar UV radiation. O2 provides some shielding, but O3 or ozone provides most of it. Most ozone is located in the ozone layer at an altitude of 25 kilometers. Shielding is provided by the absorption of UV photons by oxygen molecules, both O2 and O3, and their resulting dissociation. Single oxygen atoms combine with O or other oxygen and O2 to replenish the lost O2 and O3. It's doubtful that life could exist on Earth's surface without that ozone layer. Origin of the Earth's atmosphere. Several theories to explain the origin of Earth's atmosphere. One is a release of gas originally trapped when the Earth was formed, or by volcanism or asteroid impacts from materials brought to Earth by comet impacts. Comets have a lot of water in them, so that would be why we're thinking that's where the H2O came from. Also, you can see the different gases released, water, carbon dioxide, nitrogen, when we have a volcano. So the early atmosphere was much different than that today. Early atmosphere contained much more methane and ammonia. Solar UV was intense enough to break out H from the CH4, NH3, and H2O, leaving carbon, nitrogen, and oxygen behind while hydrogen escaped into space. Ancient plants further increased the levels of atmospheric oxygen through photosynthesis. All right, air and ocean circulation. In the absence of any force, an object will move in a curved path over a rotating object. This apparent curve motion is referred to as the Coriolis effect. All right, here's a Target store. No, just joking. It's ridiculous. So here's the target area, and you can see how that would move just because of the Coriolis effect. Everything wants to move in a circular pattern because of the Coriolis effect. And the Coriolis effect is generated by the Earth rotating. The Coriolis effect is responsible for the spiral pattern of large storms, as well as their direction of rotation. The trade winds that move from east to west in two bands, one north and one south of the equator. The direction of the jet streams, narrow bands of rapid, high-altitude winds, and the deflection of ocean currents creating flows such as the Gulf Stream. So the more rapid the spin equals a higher force or a stronger Coriolis effect. The faster the spin, the more dramatic this effect. The atmospheric band structures on the storms of rapidly rotating Jupiter, Saturn, and Neptune are due to the Coriolis effect. Precession. As the Earth moves around the Sun over long periods of time, the direction in which its rotational axis points changes slowly. The changing in direction of the spin axis is called precession. Precession is caused by the Earth not being a perfect sphere. Its equatorial bulge allows the Sun and Moon to exert unbalanced gravitational forces that twist the Earth's spin axis. The Earth's spin axis precesses around once every 2,600 years. Currently, the spin axis points at Polaris, but it will point nearly at the star Vega. Precession may cause climatic changes. What does this mean? Let me move back here a little bit. Well, let me see something. Okay, so what happens is just like a top, and they're going to show a spinning top here. As the top spins, it eventually will wobble. That wobble is known as precession. Okay, and what happens is right now the North Pole is pointing at Polaris, but it will not always be pointing at Polaris. Eventually, the North Star will change. Okay, these North Stars, the North Star changes. Right, it started here, then here, here, and today it's right here. So as it moves, as it wobbles, you can see that the North Star will change. It takes it a while. In 4000 BC, it was in this area. Today, it's Polaris. In the year 8000, it will be here, more in this area. And then in 14,000, in the year 14,000, it will be Vega. So it changes slowly. And that, my friends, is the end of the notes for Chapter 6, the Earth.